Guys, we're going to take a look at this application of thermodynamics because it just, parts of it may appear on the AP exam, and there are some equations used in here that you'll see on the formula sheet. So just in case, I want you to see this because we'll kind of be able to review a little bit about equilibrium as well. Hope everyone's doing well. And if you will just download the notes on Canvas, again, if the password's molar mass 18. So basically what we know about free energy so far is that it has to be less than 0 for a reaction to be thermodynamically favorable or to proceed in a given direction, and that the free energy is the maximum amount of work that can be done by a system. So what we want to take a look at today is that a system at equilibrium, a system will be at equilibrium when it is no longer able to do any work, or the delta G is 0. And remember, at equilibrium, forward and reverse reactions are still taking place, but net changes in concentrations don't happen. So it turns out that the equilibrium constant, KEQ, is directly related to the change in free energy. Now, I'm not really going to talk about the graphs much, and so I'm going to skip a couple slides, so we're going to skip that one. But we do want to look at the fact that when delta G is less than 0, the process will favor products at equilibrium. So that's a good piece of information to tuck away. All right, so the KEQ is greater than 1. The reaction will proceed to equilibrium in either direction. And the reaction, this term is exergonic, okay? The term exergonic. And exergonic means, the definition of it is that delta G naught is less than 0. Again, I'm going to blow through the graphs, but let's talk about endergonic reactions. Endergonic is going to mean that our delta G is greater than 0. This process is going to favor reactants at equilibrium, and the reaction will proceed to equilibrium in either direction, but it is non-thermodynamically favored, and it will produce products if the system initially contains only reactants. If the products are removed, the equilibrium will shift according to Le Chatelier, and then you'll produce more products. So remember, hey, what's delta G again? All right, delta G naught means that it's at standard state. Standard state would be a 1 molar concentration and a temperature of 298 Kelvin, which is 25 degrees Celsius. Because equilibrium exists at other temperatures, we can use the same equations to calculate delta G at other temperatures, and usually you'll see that as delta G naught with a temperature. So again, delta G is the maximum amount of work that can be done by a system as it moves from 100% reactants in their standard states to 100% products in their standard states. Now we're going to relate delta G to KEQ. So this first equation right here, it's always been given on the formula sheet for the College Board exam, and it can be used to solve for everything except KEQ. And it's basically used to solve for delta G, perhaps. The second equation basically is the same as the first. It's just rearranged. And this is the one that you'll use to solve for KEQ. The first equation it will be given to you on the College Board exam. The second equation, this one right here, you will have to either memorize it, and as you know, I'm not a memorization fan, and so just know how to rearrange. Know that natural log is e to the whatever, and then it would be a negative delta G over RT. So basically, if we want to estimate KEQ, if delta G is positive, the system will contain mostly reactants. So basically, the curriculum, College Board curriculum, said that you kind of need to know uh, how to kind of use an equation like this and be able to do it in the multiple choice section of the exam where you don't have a calculator. A couple things to notice here. Let's see, we're using right here 8 joules per mole Kelvin instead of 8.314. And then for temperature, you'd kind of want to use an estimate of 300 Kelvin just to kind of make the math a little bit easier, especially if there's a multiple choice question. So again, since you don't have a calculator on the AP exam, in the multiple choice section of the AP exam, you would just make some of these numbers kind of round them off a little bit. And so if basically if our delta G is positive, the system will contain mostly reactants when it reaches equilibrium. It also means it will have a relatively small value for KEQ. Because remember, KEQ equals products over reactants. So the more positive the value for delta G, the further to the left the equilibrium will lie. If delta G is negative, the system will contain mostly products. When it reaches equilibrium, this will also mean that it will have a relatively large value for KEQ. If you remember, KEQ is products over reactants, so if you have mostly products, you will have a larger KEQ. The more negative the value for delta G, the further the equilibrium will lie to the right. So the delta G value can help you determine the equilibrium position. So looking at this example, for a certain reaction, the delta H is negative 20 kilojoules. The delta S is minus 400 joules per Kelvin at 25 degrees Celsius. Which of the following statements provides the best description of the system at equilibrium? And so we can figure out the delta G, if you remember that delta G equals delta H minus T delta S. I will caution you again. Notice our enthalpies are often given to us in kilojoules, while our entropies are given to us in joules. And so it's going to become really important to convert that before you go ahead and calculate a delta G. And so let's estimate delta G0 is going to be equal to our delta H, okay, and that's, let's make that joules. So negative 20 joules, there's 1,000 joules in a kilojoule, so let's make that 20,000 joules. Then we won't have to do anything else. I think that's a little easier if we didn't have a calculator. And then our temperature, again, 298, but for not having a calculator purposes of estimating, 300 Kelvin, and then negative 400 joules per Kelvin. And so it would be negative 20,000 minus 12,000, I think, if I did that right. 400 times 300, 4 times 3 is 12, and then have 4 zeros, right? Oh, did I do that right? You should get, anyway, when you do this math, you should get a positive 100,000 joules. And so our delta G is positive. And if you remember which of these choices, then what will we have if our delta G is positive? The system will contain mostly reactants. And so on a multiple choice, you may be asked to do some of this and just go ahead and kind of do an estimate type of thing. This one's relate delta G to KEQ. For the above reaction, delta H is negative 198 kilojoules per mole. Delta S is negative 188 joules per mole Kelvin. So what is the value of Kp at 298? So step number 1 is to find the delta G. And so delta G equals delta H minus T delta S. And so that will equal, we'll make this joules. So negative 198,000 joules minus our T is 298. So 298. And then our S is minus 188 joules per mole Kelvin. And if you do that, you should find out that delta G0 is equal to 142,000 joules. And so that is our delta G. Next, using that delta G, we can find Kp. So Kp is like KEQ, and so that's going to be e to the negative delta G RT. And so my Kp will equal e to the negative. Pay attention to your signs here. We got 142 joules per mole. And make sure your units work. We'll use our 8.314 joules per mole Kelvin. And our temperature of 298 Kelvin. And so our units, we'll pay attention to your units. And do this in your calculator. Make sure you can get the answer. Your Kp should be 7.78 times 10 to the 24th. And so this equilibrium, the value of the Kp value, shows that the equilibrium lies far to the right. If you remember, our delta G was negative, which would predict we'd have mostly products. And with a Kp like that, that is indeed the case. Then for the above reaction, it gives you a Kp. It says the Kp equals 36.5 at 400 Kelvin. Find the delta G. So delta G0 is going to be equal to negative RT, natural log of Kp. And so the delta G0 will equal negative 8.314 joules per mole Kelvin. Times 400 Kelvin times the natural log of 36.5. Put this in your calculator. Make sure that you can get 1.20 times 10 to the 4th joules per mole, which you can do as kilojoules. So you can say that delta G is equal to 12.0 kilojoules per mole. So looking at the free energy then of dissolving things, kind of like we took a look at in equilibrium a little bit in thermodynamics, it's going to require energy, just a reminder, to break a bond or to sever intermolecular reactions. And so this is just a quick review of the energy changes that occur when bonds are broken. And so remember, energy's always evolved. Potential energy decreases. This is kind of a review. So our enthalpy, delta H, enthalpy of dissolution, ionic bonds have to be broken. Hydrogen bonds between some of the water molecules have to be broken when we go from a solid to a liquid or a liquid to the gas. And so both of those are endothermic processes. And ion dipole forces is an exothermic process. Looking here at sodium and chloride ions, ions basically drag water molecules around with them in solution. And so ion dipole forces are established between the ions and the surrounding water molecules. So these are ion dipole forces. Between the water molecules and the ions. And so if the overall process is endothermic, more energy was required to break the ionic bonds and the hydrogen bonds than was released when those ion dipole attractions formed. So most ionic compounds, dissolving them is endothermic because the ionic bonds are very strong. This is the type of thing that you would have to say if you predicted whether something would dissolve or not, or if the energy, you'd be given some data where the energy of dissolving one thing was more or less than the energy of dissolving something else. And so when you answer things like that, think of it in terms of, hey, the strength of the bonds that are having to be broken for this dissolving to happen. Especially if you're given a delta H, you can determine if the reaction was endothermic or exothermic. And so if it's endothermic, remember that means our delta H would be negative or positive if it's endothermic, and more energy would be required to break the ionic bonds and the hydrogen bonds than is released when you make the products. If the overall process is exothermic, more energy is going to be released when the products are made, so to speak, when the ion dipole interactions are established, rather than was required to break the ionic bonds and the hydrogen bonds. An ionic solid's very organized, and a solution containing the same ions much more disordered. Yay, delta S disorder. Delta S is positive, usually when the ionic solid dissolves in water. And looking at entropy, when an ionic compound dissolves in water, the entropy will usually increase greatly given a positive value for delta S. Basically, the crystal lattice of the ionic compound breaks apart, and the ions are free. They are free to move around. So delta S can be negative sometimes for small ions with large charges. Aluminum is a good example of that. I don't expect that you'll see this on the AP exam, but just in case, it kind of gives you some information there. Looking at the free energy of dissolving something. So here's our solid. We've dissolved it into its, if an ionic compound is soluble, the delta G is negative and the equilibrium lies to the right. So this is a little hint for you if you're given some information about a reaction and you're asked to determine if something dissolves or whatever, and you're given the delta G. If the delta G is negative, basically the compound will dissolve. If an ionic compound is not soluble, then the delta G will be greater than 0 and the equilibrium will lie to the left. So for example, an unknown ionic compound dissolves in water. Okay, so that tells you probably the delta G is negative, right? During the dissolving process, the temperature of the solution decreases. Predict the signs, positive or negative, for delta H, for delta S, and for delta G. All right, so delta H, delta G, and delta S. And so I already told you delta G is negative. And why do we know that delta G is negative? We know that delta G is negative because the compound dissolves in water. And so let's see, if the temperature in the solution decreases, what had to happen? Well, basically our system had to take energy from the surroundings. If it had to take energy from the surroundings, What sign does that make delta H? Hopefully you said that made delta H positive. And then we are dissolving an ionic compound in water. So what did we do to our entropy? Did it become more disordered or less disordered if it's a dissolving process? That should be positive. And so again, our delta G is negative, and remember delta G equals delta H minus T delta S. So for today's assignment, if you will go to the 9.5714 problems, I'd like you to do problems 1 through 4, then number 6 and number 8, and upload those to Canvas by tomorrow at midnight. Tomorrow I will give you some more information about how we're going to get ready for the